Alright, so when current flows in the circuit, I get a current through this inductor, and because this is just a coil of wire, it's like a solenoid. Basically, most inductors are just a coil of wire like a solenoid. It's a cylindrical coil of wire. And when I get a current that flows through this inductor, I get a magnetic field. So there's a magnetic field that's generated by this inductor. And as a result, so B field is in the inductor. In fact, it is a changing B field. And as a result, the inductor generates an EMF. That is, it's like a source of voltage that is opposite the EMF of the battery. Alright, so you can imagine I have this EMF driving a current in this direction, and as that current picks up, this inductor will generate a magnetic field, and that magnetic field will cause an EMF that will oppose the EMF of this battery. So I have the battery driving my electrons in one direction, and then that inductor is going to drive them in the opposite direction. So it's going to like impede the EMF of the battery. Remember, this is just from Faraday's law, that the EMF of this inductor is equal to, well, Faraday's law said that the EMF is equal to the change in the magnetic flux with respect to time, but we can also say that the EMF of the inductor is equal to negative L times DI times DT. I think we've already had that one. Yeah, so if you remember when we defined our inductance was defined as phi b over t. So since I know that my EMF is d phi over dt, I can put these two together and I get this expression for the EMF of the inductor. So my current changes, and that causes a change in the magnetic flux, which causes this EMF in my inductor. Right, so I get this change in current that leads to this EMF in the inductor. Now, initially, the current rises slowly. Because of this EMF from the inductor. So normally when we're just talking about normal circuits, like the resistors and batteries, we imagine that the current is instantaneous. Like if we just have a normal resistor circuit, when I hook up the battery, I instantaneously get the current, whatever the current is in the circuit. But here, because I have this inductor that's actually slowing down the current, that's giving us this opposing EMF, it's going to slow down the current, and so that current will just rise slowly. After a long time, depending upon the inductance of the inductor, the current approaches its maximum value. which is just E over R, the EMF over R. Remember, this is just from our Ohm's law, phi equals IR. After this long time, the B field in the inductor stops changing. Remember, it's a changing magnetic field or a changing magnetic flux that causes an EMF. And after a long time, that magnetic field stops changing because my current reaches this maximum value and it doesn't change anymore. So then I no longer have this EMF, and at that point, EL goes away, and the inductor just acts like a piece of wire. Alright, so after a long time, that inductor, it's like it's just a piece of wire. It is just a piece of wire, right? It's just a piece of wire that's coiled up into a solenoid. But after a long time, because that current is no longer changing, and the magnetic flux is no longer changing, the magnetic, the EMF goes to 0 for the inductor. And then it's just like it's a normal circuit with just a resistor and a battery. Alright. We can look at this. You don't take differential equations, do you? You do? Okay, well, you'll get into that course, I guess, next semester. Is that right? Next semester? Oh, you do Calc 3 next spring. It was probably by far the hardest math class that I've ever taken. Differential equations. Like, I completely, most of the course, I was just like, I have no idea what's going on in this course. So, good luck with that. I hope you do well. What's that? No, I didn't take that class. Are you taking it? I think yeah, I don't know. I didn't take that class. I think you have to be a different kind of person to take that class. I'm not that person because I've talked to math majors and they really like it. They like that class a lot. But they say it's like a different level of understanding. It's just sort of a different approach with mathematics. I hope you like it. I think you might like it. No. Are you doing a minor? Is that why you're taking it? Yeah. Okay, so if we look at, anyway, we'll see some simple differential equations in this section. If we think about this, this circuit, I have my EMF, I have my resistor, IR, and then I also have this EMF of the this inductor, which remember is L di dt. So I have 3 elements in this circuit, and the EMF of each is changing. Or rather, I have a voltage drop across each one, and I can do my loop rule by this. If I go around, it's going to be E, that's just the EMF of the battery, minus IR minus L di dt. And this is all equal to 0. This is just the loop rule. We saw the loop rule a couple of chapters ago, right? That the sum of all the potentials around this loop has to equal 0. And that's true when I throw in the inductor. But now it's different because with the inductor, the current changes with time, or rather the EMF is dependent upon the current changing with time. So when this current changes with time, when this goes to 0, there is no longer an EMF. But while it's changing, it generates this EMF, this voltage. Alright, so I want to solve this. This is a first order differential equation, and I just want a solution for this. What is a solution for I such that this equation is true? Alright, we're not going to solve it. I'm just going to tell you what the solution is. Is that okay? That is what it is. I'm not going to solve it. So my current, the solution for this is that the current is E over R times 1 minus e to the minus RT over L. I said in differential equations, you'll talk about how to solve these. But in this circuit, my current is this expression for the current solves this expression and makes that a true statement. That the current is the voltage of the battery divided by the resistance times this 1 minus e to the minus RT over L. This should look somewhat familiar to you. What does this remind you of, this expression? What is it? Right, for RC circuits. In fact, the expression, or the function, looks the same. If I look at the function of current or voltage versus time, it's going to be the same for both current or voltage, because they're linearly proportional to one another. It looks like this. This is just the current in the circuit. This is going to approach some maximum value. That maximum value is E over R for current, R just E, the EMF of the battery for voltage. All right. All right, so after a long time, as I said, I is equal to E over R, as if the inductor is just not there at all. All right, so similar also to capacitors, after you turn the circuit off, that inductor will actually generate a current for a certain amount of time, and it'll decay. So I have this growth curve, and then after I turn off the battery, that inductor holds energy. We'll see that in just a bit, how it has a certain amount of energy in the magnetic field, and that will cause the current to continue. So after you turn the circuit off, the current exponentially decays. Right, so you could go back to that loop rule, and if I just get rid of E, the EMF of the battery, so I come back to this up here. Now if I take out this, then I want to know, well, what is a solution of this that will make this equation true? This IR plus L di dt equal to 0. And the function for I that causes this to be true looks like this. E over R times e to the minus t over tau. Now, this is the time constant of our inductor. And the time constant for that is tau L is equal to L over R. All right, so this is our time constant. This is our current with respect to time for a decaying circuit, or for a decaying current. And if I look at this, my current versus time, it's going to look like this. So this is just like we had for RC circuits, very similar here, except now instead of being a resistor and a capacitor, we now have a resistor and inductor. But it looks a lot the same. So we're sort of interchanging current between these two things. All right? Or it's like the inductor actually holds energy, just like the capacitor holds energy. Let's do a quick example. These are pretty straightforward. Sort of understanding these can be difficult, I think. Is it difficult to understand sort of how these inductors are working? Yes? No? All right, well, the inductor holds this magnetic energy, and that energy it uses later. So after you turn off the circuit, in a similar way that the capacitor held charges, and so it held energy within it, the inductor also holds energy and stores energy. And then after you turn off the battery, then it releases that stored energy. And a lot the way that the capacitor did, though it's a different type of stored energy. Instead of being energy stored by the electric fields of the capacitor, this is energy stored by the magnetic fields of the inductor. We'll get into this more when we look at LRC circuits. Let's do an example. Let's say that we have a circuit that looks like this. battery, a resistor, and an inductor. By the way, the symbol for the inductor, you can see a symbol sometimes like this, or you might see a symbol that looks like this, and I'll use both. The top one's sort of easier to draw, but you can also see it more like this, and this sort of represents physically what the inductor is, but it's just a coil of wire, it's a solenoid. Alright, so let's imagine I have this circuit. I have 0.37 ohms. I have an inductor of 53 millihenries. And I have some EMF. I want to know how long does it take to reach half the equilibrium current. After I turn on this circuit, I have a switch, it's open, and then I close it, and I start this circuit doing what it does. I want to know how long does it take to reach half the equilibrium current. Why don't you take a couple minutes and start on this. So you want to start with that expression that we derived, that I is equal to E over R 1 minus E to the minus RT over L. Or T over tau, where tau, remember, is equal to L over R. And you want to find the time when my current is equal to half the equilibrium current. What is the equilibrium current for this this resistor or this circuit? At the equilibrium current, what happens to the inductor? How does it act? It's just E over R, right? So when I've reached my equilibrium current, what is the inductor like? What does it do? It doesn't do anything at all. It's just like a wire. Because once it gets up to that maximum current, the current doesn't change anymore. The inductor does not generate a magnetic field, because an inductor requires a changing magnetic field to generate an EMF or a current. And so my maximum current is just going to be equal to E over R, my EMF over the resistance. Go ahead and try this out. You'll need to use your natural log function on your calculator. If you're not familiar with that, it should be a button that just says LN on it. You know, if you get a number for your time. I get a time for me? Not yet. I'm going to start here. You know that my current is half of E over R. That's equal to E over R times 1 minus E to the minus T over tau. These cancel. If I take the 1 over, I get a negative 1/2 equals negative E to the minus T over tau. Make those both positive. You don't have to do this, but it makes it a little bit easier if you say 2 is equal to E to the positive T over tau. All right. How do I get rid of that exponential? If I want to solve for T, how do I get rid of the exponential? Right, I take the natural log of both sides. So I do natural log of 2, natural log of this. That cancels out there. And then I get natural log of 2 equals T over tau, excuse me. What is tau equal to? What is tau? L over R. Anybody know what that is? 0.53, that's right. Don't forget to convert your millihenries to henries divided by point. What is it? Okay, we'll just get to that. All right, and then we just solve for T. So T is natural log of 2 times 0.143. I don't know what that is. Somebody tell me what it is. I think I know what it is, but. Okay, 0.099, we'll just call it 0.1 seconds. All right, so it takes 1/10 of a second in order for this to reach its equilibrium current. I think these are pretty straightforward, but the hard part is solving these exponentials, because you might not do that very much. Is that true?
It takes 0.1 of a second to reach its equilibrium, or half its equilibrium?
No, to reach half of its equilibrium. So to reach the equilibrium would take twice that. All right. All right, let's look at another one. Let's say that I have a circuit that looks like this. All right, I have 1 millihenry, 2 ohms, 2 ohms, and 2 ohms up here, and 1 millihenry. And down here I have 12 volts. A couple of questions. What is the initial current through this circuit? What is the initial current through this circuit? Now remember, when I'm talking about inductor circuits, and I'm thinking about the current versus time, the way that it grows looks like this. So what is the initial current through this circuit? The total current, that is the current that comes off of this 12-volt battery. What is my initial current equal to? Take a gander at that. Well, first you need to answer the question of what is the current. We know the current in this branch, right? What is the current here? 6, right, yeah, 6. Yeah. So because I have 12 volts and 2 ohms, I have 6 amps. So now I need to know what is the current here and what is the current here. Remember, all three of these parallel structures, they operate independently. So I have that thing going on here, and I have that thing going on over here independently. All right. So initially, what is the current through this circuit, through this part of the circuit? At T equals 0, what is our current? is 0, right? Because initially I have no current at all through that inductor. All right, and then likewise up here I have 0 current. So what is my initial current coming off this battery? 6, right? So I have 6 amps initially. I have 6 amps going just through that middle 2 ohm resistor, and that's all I have. So I have only 6 amps as my initial current. What is the current after a really long time? Not 6 amps anymore, no. It's a good guess, but no, it's not 6 amps. What happens after a long time to those inductors? How do they now begin to act? They're just a wire. They're just a wire in your circuit. So it's now what? It's going to be 18. Because where I had 6 amps here, I'm also going to have 6 amps here and 6 amps here as well. Just 6 plus 6 plus 6 will be 18. All right, so the current after a really long time will be 18 amps. And then in between, you can do like we did in the previous problem, where you find the current at particular times, because the currents in each of these branches is going to follow this function, that 1 minus e to the minus business. Okay, so in between, you can calculate the current at any device at a particular time. All right, but they're going to go between 0 and 6 amps for those inductor branches. All right, we sort of talked about this, and we're going to get into LC circuits, where I have an inductor and a capacitor. But first, we just need to, I'm not going to derive it, I'm just going to tell you the expression. But there is energy stored in magnetic fields. And I sort of alluded to this before, but it's really a lot like the energy that we store in a capacitor. Right, there's energy stored in that capacitor, but the energy is stored in the electric fields of the capacitor. There's energy in the electric fields. And if you remember when we did this with capacitors, but that energy in the electric fields, I'm going to call it UE here, for the electric field, was equal to, what was it, 1/2 CV squared. All right, so this has already occurred, like we've seen this before with capacitors. And we sort of talked about the energy being stored in the charges, but that's not really the right way to think about it. Really, the correct way to think about it is that that energy is actually stored in the electric field, which is inside of the capacitor, in between those two metal plates. All right, so in a similar way, when we have these coils of wire, these inductors, they also store energy in their magnetic fields. And the magnetic field energy, the potential energy, is equal to 1/2 L times I squared. You can go through and derive it. We're not going to do it here, but you can. But I just want to get to it now because we'll see it in LC circuits when we have a capacitor and an inductor, and those two things are going to sort of trade back energy back and forth. So you have a couple of clicker questions. Just a couple, I think. Actually, let's see. Now let's try this one. Okay, the potential at A is higher than the potential at B. What is the, which of these statements is true about the current? Okay. First of all, I know that the current is changing or not changing. If what I have here is I have an inductor that is generating an EMF. And does that mean that the current is changing or not changing? It has to be changing. So I can get rid of some answers here. I can get rid of A and C. So this one is not an option, and this one is not an option. Now let's think about this and how it looks as a battery. Like if I were to put in a battery here to represent the EMF, what would it look like? Would it have the high potential side followed by the low potential side, or the other way around? Which would it be? Would it be like this? Let me draw it. Would it look like this? Or would it look like this? Okay, well, where is the potential higher? At point A or at point B? Because where the potential is higher is where this big side is going to go. Where is the potential higher? Point A or point B? Point A. Point A, right. So if I were to represent this by a battery, it's going to look like this. Right, so I can imagine this as like the EMF that's generated by this inductor. Right. Now, remember that the EMF that is generated by the inductor is going to oppose the direction of the EMF that's driving the current. Remember what I'm talking about? Like we had a circuit before where I had a battery, I had a resistor, and then I had an inductor. And this battery was driving a current in this direction, and then the inductor had an EMF that was in that direction. All right, so what this is asking is what is the direction of this driving current that's generating this EMF in the inductor? What is the direction?
A to B.
Huh?
Flows from A to B.
That's the question, right? All right, is that a statement or are you asking a
I
question?
thought I was making that a statement.
Okay. Okay. Right.
Well, the inductor, the high potential is on the left, so the battery is going to be driving the other way.
Right.
So it's going to flow from A to B.
That's correct. Yeah. So the current is flowing from A to B. So that gets rid of option 4, which a lot of people. Well, option 4. All right. All right. So now I want to ask the question: is this current increasing or decreasing? It's what? Okay, well, let's go back to our Faraday's law and the Lenz's law, like where we had the decreasing current, or we had a decreasing magnetic flux. Let's see. So remember we had this loop of wire. And we said if we have a magnet that's going into this loop of wire, and if it's going in this direction, that's an increasing flux, and as a result, the magnetic field that's generated by this is going to be in this direction. But if it's being pulled away, that's a decreasing flux, and in this case, the magnetic field of the loop is going to now be in this direction. So my magnetic field here is going to oppose, or excuse me, what was I saying? Oh, so if my current is increasing, that means that the EMF will oppose the current. If my current is decreasing, that means that the EMF will be in the same direction as the current. And that's sort of a similar thing here. Here, my current is, or excuse me, so let's just rewind. So if the current is increasing, the EMF of the inductor opposes the EMF of the battery. If the current is decreasing, the EMF of the inductor is in the same direction as the battery. All right? So what is the direction of the current here then? All right, sorry, is the current increasing or decreasing? It's going to be increasing, right? I have an increasing current. All right? So the answer is what? E is the right answer, right? All right, so a few more seconds. I'll stop at 6. All right, let's look at this next one. Rank these in order from largest to smallest, the time constants. And remember the time constant was it L over R? Is that right? Yeah. So the time constant is the inductance over the resistance. Rank these in order from largest to smallest by the time constants. Remember, the time constant characterizes how long it takes for that current to reach its maximum value. Okay, doing pretty well on this. A lot of you have the right answer. The one with the longest time constant will be the one with the biggest resistance or the smallest resistance.
No, small.
Right. If R goes down, that means tau goes up. So the one with the longest time constant, that's the one on this end, will be the one with the smallest resistance. And the one with the smallest resistance is which one? It's the third one, right? Because remember, resistors in parallel, when I add up these resistors in parallel, the equivalent resistance is going to be smaller than any one of the resistors. So this has some smaller resistance than this, even though it has more resistors, because they're in parallel. And then I need to differentiate now between these two to fit between B and B. Is what? Right, I have a bigger resistance for T2. So where does it go? In the middle or at the end? At the end, right. It has the shortest time constant. So D is the right answer. Most of you had that. Just a few more seconds. 220. Very good. All right.
Are these posted on the website?
I'll put them up. They're not right now, but I'll put them up. Let's see. All right, I think we'll stop there. We'll pick up with LC circuits next time. But I don't want to get into that new topic. How was your weekend? Okay.